Let's get started. So, Chapter 7, not drastically different from Chapter 6. We're just going to look at more specific scenarios. So let's remind ourselves quickly of Chapter 6. What were we focused on in Chapter 6? You remember? What do you remember about Chapter 6?
Work energy theorem.
Work energy theorem. So we learned how to calculate work with this integral here. The work done in going from some point A to some point B was this integral. And we had the work energy theorem, which gave us that the total work done on a system, work total done on a system, we showed that the total work done on a system was equal to the change in its kinetic energy. Its kinetic energy at the end point minus its kinetic energy at the start point, or just equal to the change in its kinetic energy, right?
Yeah.
And we calculated a lot of different works done by different types of forces, and we calculated a lot of kinetic energies. So now we're going to make a distinction between two types of forces. One we're going to call conservative force, and another one we're going to call a non-conservative force. So intuitively, a conservative force is a force that the amount of work to get an object from point A to point B is independent of the path. That's conservative force. A non-conservative force is where it depends on the path. So imagine I've got to move a table, I've got to slide a heavy chair from here to there, and I slide it on this weird path like that and then get to my point. That takes a lot more work than just sliding right to the point, right? However, if we think about lifting this heavy box up, it's just as much work for me to lift it up like this as it is for me to lift it up like this while I'm walking forward, even though it makes the path much longer. So in lifting an object, it doesn't matter the path if my start and end point are the same. It doesn't matter the path I take, the work is calculated based off of the difference between the start and end point. Another way to think about conservative forces is they're forces that if you do work on them, you can somehow get that work back. If I take a heavy box and I lift it up in the air, I can somehow get the work back out of that box by letting it fall. If I slide a chair from point A to point B and let go, it doesn't slide back to point A. Once that work's been put into the system, it's gone. There's no way to get it back out. So gravity, somehow if I put work into the system, if I put energy into the system, I can somehow get the energy back out. Friction, I can't. Is there anything weird about what I'm saying so far?
Isn't it both work?
Both are work. So it takes work for me to slide a box from point A. Here's one way to think about it. I take a box and I slide it from point A to point B, and then I slide it back to point A. My total work is not zero for sliding a box. I have to overcome friction. Let's say the force of static friction is 100 newtons, and I slide it for 1 meter. That's going to be 100 joules of work. I slide it back. Now I've done 200 joules of work. It was just as hard for me to go from point A to point B as it was from point B back to point A.
Okay.
Now let's think about lifting a heavy box. I lift a heavy box, and let's say it's 100 joules to lift it up like this. Then, when I put it back down, how much work do I do?
None.
Negative work.
Negative work.
Negative work. I'm doing positive work. Now I'm doing negative work. And it's doing work on me. I'm doing work on it. It's doing work on me.
Is it doing the same amount of work that you did on it?
Yes. And so, don't confuse I'm burning calories with it's doing work on me. I might get tired lifting this up over and over again all day, up and down, up and down, up and down, but the net work when it's all said and done is zero. When I slide a box all over the place, the net work done is not zero, even if I end up back where I started.
Why?
Yeah, so the intuition there is, sliding a box, once I put that energy into the system, there's no way to get it back out. Okay. Here, let me give you a more concrete example. Maybe this energy thing is throwing you off. Imagine I've got like a little hydroelectric generator here. So I dump water. If I dump water on it, then it spins a wheel, which will spin some magnets, which will run a light bulb, something like that.
Okay.
And let's say it's perfect, so that all the energy that goes into that wheel, it will all be converted to the light bulb. So if I take a bucket of water and I lift it up in the air, I just put energy into that system, lifting up that water. I can now dump the water out and let it spin that wheel and generate electricity. I can get energy back out of the system.
Yeah.
Because I put energy into the system by lifting that water up, and now I can get energy back out somehow. I can get it back out by just letting it fall, and it's going to have a bunch of kinetic energy while it hits the floor. Or I can let the water spin a wheel, and I can let it generate electricity and get energy that way. But I can get energy back out of the system.
And that's the conservative?
Because, yeah, that's the conservative force. That system can still do work. When I lift up that bucket of water, that water can still do work.
Okay.
Right?
Yeah.
And whether it's spinning it on a wheel or I'm just setting it back down, doesn't matter. That's the work it could do. It did its work. But the point is, there was energy in the system that could somehow be tapped into and pulled back out. When I slide a box from point A to point B, there's no way to now get work out of it.
Yeah.
If I lifted it, now there's a way to get work out of it.
So how can you get work out of that other than gravity?
We only could with gravity in this situation. Another conservative force would be a force of a spring. I put energy into the system by compressing the spring, and now I can get energy out of the system
By letting go.
by letting go. I can use it to launch a ball, or I can let it push me, or whatever. So conservative force, two intuitions for it. If it's a conservative force, the amount of work you have to do to go from point A to point B is independent of the path. That's like lifting an object. Another intuition for a conservative force. A conservative force enables you to get energy back out of the system that you put into the system. The energy is not somehow lost.
Okay.
Two intuitions there.
Yeah.
Okay. So, in chapter 6, we were just dealing with a bunch of different forces, different works, just calculating works. Today, we're going to be particularly interested in these conservative forces and the work that they do. So we're going to be particularly interested in gravity and springs. Okay. And, well, we'll just start with that for a second, and we'll go from there. So with gravity, so we set up this scenario here where I've got some object. I try to make it look 3D. So it starts out here at point A, and it ends here at point B, which is in a drastically different position. And here's the path that I lift this object along. Good? Okay. So now, this is lifting an object. It's being moved, and just gravity is the only force acting on this object as it's being moved from point A to point B. And so question, what is the work that gravity does on this object?
It's equal to the force you pick up.
Well, we'll calculate the work that gravity does exactly like this. Here's our definition for how you calculate work, right? So let's write out what these vectors are really quick, and then we'll just calculate it. So for my net force on this thing, as it's going from point A to point B, in the x direction, what's our forces?
The x direction.
Yeah. Oh. I accidentally called this. Sorry, we're going to make this a little bit of a weird coordinate system. I just want y to be up because that's what we're typically used to. But I also want to draw three-dimensional. And we'll replace the z with y when it's all said and done. Okay, we'll be fine. Okay, so in the x direction, what's our force, our net force?
I don't know.
In the x direction coming out of the board. So here, I'm holding this marker, right? Think about all the forces acting on this marker. We'll call the x direction that way, the y direction that way, the z direction that way. What are the net forces in the x direction acting on the marker?
Right now?
Yeah,
Nothing.
nothing. What about in the y direction?
Nothing.
So it's all in the z direction.
No, there's nothing.
The net force is 0 because I'm holding it. But now imagine that I were moving this object like this, There's no x and y. There's no x, there's no y, there's just z. I'm moving with constant velocity.
Oh.
So the only force acting on it is gravity. Right? Moving with constant velocity, it's not accelerating, it's not slowing down. So we've got some particle moving along some random path with only gravity pulling on it.
Doesn't the x still change a little bit?
No, constant velocity will stay in the x direction. So our force, net force in the x direction is 0. In the y direction we have negative mg. And in the z direction we once again have 0. Oh, no, I forgot. I'm going to get confused if we do that. Sorry, we need to call up y.
Okay.
Sorry. Okay. For our dr vector, we already know what this is. This is just dx, dy, dz. And it's some infinitesimal change along the path. An infinitesimal change in the x, y, and z direction, right? So now when we're calculating the work that gravity does on this particle, moving it from point A to point B, calculating the work gravity does on this thing, moving it from point A to point B, we are going to have the integral from A to B of our force there. Well, let's just think about the dot product of these two real quick. Dot product is you multiply the x with the x, the y with the y, the z with the z, and you add them together, right? When I calculate that dot product, this is just going to come out negative mg dy, right?
Yeah.
Okay, perfect. Now we just calculate this integral.
Okay.
So it's just going to be negative mg times y at point B minus y at point A. You with me?
Mm-hmm.
Perfect. We also knew that this work was equal to 1/2 m the velocity at b squared minus 1/2 m the velocity at a squared. We got that from last week, right?
Yeah.
So, erase this side of the expression really quick. This is then equal to this thing. And I'm going to distribute the negative mg across both these. You good with that?
Mm-hmm.
Okay, so now I'm going to put all my terms that have an a in them on one side and all my terms that have a b in them on the other side. So we have 1/2 mvb squared plus mgy sub b is equal to, moving this to the other side, 1/2 mva squared plus mgy sub a. You see that?
Okay.
This right here, we call the kinetic energy at point B. Plus, this we have a special name for. We call it its gravitational potential energy. The gravitational potential energy. And let's really quick get a feel for what this number is before I continue explaining here with just one really quick example. Let's say I lift this marker 1 meter in the air. Let's say it weighs 1 kilogram. And I have it 1 meter in the air. You with me?
Yeah.
How much work can I possibly get out of this thing if I let it fall?
Just 9.8.
Just 9.8. And what did you do? You did its weight times how high it was times g. You did mgh.
So the y is
The y is your y coordinate, how high.
yeah.
You with me?
Mm-hmm.
Okay, so that's why it's called your gravitational potential energy. So your kinetic energy at point B plus your gravitational potential energy at point B is equal to your kinetic energy at point A plus your gravitational potential energy at point A.
That is supposed to be u?
Yeah, those are U's.
Okay.
We use U's for potential energy.
This one.
Okay, so potential energy, the energy you could potentially get out of the system. Kinetic energy, the kinetic energy that the object has based off of its velocity. Notice then that from point A to point B, this sum is always the same. Your kinetic energy plus your potential energy at the beginning is equal to your kinetic energy plus your potential energy at the end.
Okay.
You see that? We call this whole quantity your kinetic energy plus your potential energy. We call it your mechanical energy. And the way that we could say this is your mechanical energy is conserved. Your mechanical energy at the start is equal to your mechanical energy at the end.
What's mechanical energy?
Your kinetic energy plus your potential energy, we call that sum your mechanical energy.
Okay.
So your mechanical energy at the start is equal to your mechanical energy at the end when you're dealing with a conservative force. When there's no work done by non-conservative forces.
Yeah.
Okay, let's go see the same thing except for this time with springs. And then we'll draw a more general conclusion. You good?
Yeah, I'm just writing that down.
Okay, so here's this scenario. I grab a spring at x1 and we pull it over to x2. So this mass has moved from x1 to x2. So let's calculate the work then that the spring does. So we're going to calculate the work that the spring does, and then we're going to and we know that the work that the spring does is also equal to the change in its kinetic energy. We also know that this is equal to a change in kinetic energy, right?
Mm-hmm.
But now we're just going to calculate this really quick. So first off, what's the force that the spring exerts on this thing? It's going to be pulling back that way, right? If the displacement was this way, the spring was pulling that way. So it's in the opposite direction of our displacement. So in this case, in the x direction, we have, and we remember Hooke's law, it's negative k times x times however far you've stretched it. Hooke's law.
Yeah.
The force of a spring is negative kx. In the y direction, once again, it's obviously 0, and in the z direction, it's obviously 0, right?
Yeah.
And we know our dr vector, once again, is just dx, dy to z. And so when you take the dot product of these two, what do we get? It's going to be the integral from x1 to x2 of negative kx dx.
Yeah.
Good? And what is this going to be equal to?
Just going to be 1/2 negative kx squared.
So minus 1/2 kx squared. Evaluated from x2, or from x1 to x2, right?
Yeah.
So it's equal to negative 1/2 kx2 squared plus 1/2 kx1 squared. Right? Now, once again, I also know that this is going to be equal to our change in kinetic energy. So I know that 1/2 m, our velocity at point 2 squared, minus 1/2 m, our velocity at point 1 squared, is equal to minus 1/2 kx2 squared plus 1/2 kx1 squared, right?
Mm-hmm.
Once again, we'll put all my 2's, how did I do it over here? We put the b's on the left, so I'll put all my 2's on the left, and I'll put all my 1's on the right. So putting all my 2's, when I say 2's, I mean my sub 2's.
Yeah.
So 1/2 m v sub 2 squared plus 1/2 k x sub 2 squared is equal to 1/2 m v sub 1 squared plus 1/2 k x sub 1 squared. All right, now guess what we call this quantity right here? 1/2 kx squared relative to spring.
1/2 kx squared.
Yeah, what do you think we call that quantity?
Kinetic energy of the spring.
No, this is the kinetic energy. This we call the potential energy of a spring. It's calculating how much energy you could possibly get out of a spring compressed that much.
Yeah.
You see that?
Mm-hmm.
So, once again, this is k sub 2, our kinetic energy at 2, plus, this time it's our spring potential energy at 2, is equal to k sub 1, plus our potential energy in our spring at 1. Sorry, I use B's and A's here and 1s and 2s there, but same thing.
But is that a stand-in for your
This was your gravitational potential energy.
gravitational?
This was the potential energy in your spring. Now, in general, we can just say your kinetic energy at B plus your potential energy at B. Are we talking about springs or are we talking about gravity? Doesn't matter. Is equal to your kinetic energy at A plus your potential energy at A. So you might have one system where somehow you're converting gravitational potential energy into potential energy of the spring. That's fine. You can plug all that into this. So you can think about this as the sum of your spring's potential energy plus your gravitational potential energy. And you can also think about that for this. So U is just a stand-in for potential energy. We don't really use U for just gravitational potential energy. We use it for potential energy. And you infer from context from the problem you're solving what type of potential energy. The point is, when you're trying to solve a problem, you take its kinetic energy at the beginning plus its potential energy at the beginning, and that's going to be equal to its kinetic energy at the end plus its potential energy at the end.
And that's mechanical energy.
Yep, mechanical energy, mechanical energy, mechanical energy is conserved. This is only the case when there are no other forces, there's no non-conservative forces acting on the system. If we throw friction into the picture, this no longer holds.
Okay.
Where do we put in things like friction?
And then non-conservative.
Well, we can rewrite this equation really quick now with friction in there. Let me see what subscripts the book uses real quick. I don't know if they use B's and A's or 1s and 2s. They use 1s and 2s. Okay, so we'll switch to 1s and 2s in our convention. Here's how you can write it in a more general way. The kinetic energy at the beginning plus the potential energy at the beginning plus all the work being done on the system is equal to the kinetic energy at the end plus the potential energy at the end. And this is the final one that includes everything. So your kinetic energy at the start, plus your potential energy at the start, plus all the work that comes into the system from non-conservative forces.
Okay.
Like if it was friction, then that would be a negative.
So that's the net force of all the other forces.
Of all the other work, not a force, work. Of all the work from all the non-conservative forces coming into the system.
Okay.
Is equal to your kinetic energy at the end plus your potential energy at the end. Why don't we have plus the work done by your non-conservative forces at the end?
Because it doesn't come back.
It wasn't conserved, yeah. It doesn't come back out. It doesn't show up on the other side. It goes into the system and somehow you can't get it back out.
Okay.
So if you add in like friction, the way that's going to show up over here is you're going to have less kinetic energy. Your object's going to be moving slower. Make sense?
Mm-hmm.
Okay. And then this sets us up for something. This is all we'll use to solve all our problems.
Yeah.
Basically. We might write it a couple different ways. Almost all our problems. There's one derivative we got actually, which is stupid easy. But for the majority of our problems, this is all you need to know. But this is getting at the doorsteps of a more fundamental concept in physics, one of the most fundamental concepts in classical mechanics, which is that of conservation of energy, period.
Okay.
So conservation of energy is a concept that there is no such thing as energy being lost, and there's no such thing as energy being created. All energy is always and forever 100% conserved. Even in friction.
Where does it go in friction?
Where does it go in friction? That's a great question. So here I've got this chair, and obviously I'm putting energy into the system, and now where's the energy now? Where did it go? Let's give you another example that might help your intuition. I've got my hands here. If I do this, I'm doing work, right? Rubbing my hands against each other, that's friction.
Mm-hmm.
What else happens if I do that?
You heat up.
They heat up. That's where the energy is going. I'm producing heat. Friction produces heat. Heat is energy. It's just energy that we can't really account for here, so we kind of ignore whatever happens to the heat. So we call it a non-conservative force because we don't track the heat produced by friction in this class. But fundamentally, all energy is conserved. There's no such thing as losing energy. I rub my hands together. Yep, that's a lot of friction, but it's producing heat. As I slide this across carpet, I'm warming up the carpet.
Where does it go after it's warm?
Those heated up photons, it goes up and it collides with an air particle, which then gives it a little bit more kinetic energy, which raises kinetic temperature is roughly a measure of kinetic energy. So the air in this room starts jiggling a little bit faster, so the air in this room has a little bit more kinetic energy. So ultimately, it's going towards the kinetic energy in the room. The air in this room is now moving a little bit faster, heating it up. My hands, the cells, everything that's made out of them, they're vibrating faster, vibrating faster, vibrating faster. They're getting more and more kinetic energy, and it's heating up the air around them. If I were to get really, really warm and then just hold my hand really close to you, you can start to feel some heat. What are you feeling? You're feeling that the air molecules that were right next to my hand are traveling a little bit faster than the other air molecules around you. They have more kinetic energy, and you're feeling that. We'll calculate exactly how to think about temperature in terms of kinetic energy later. But the fundamental concept, one of the most fundamental concepts in all of physics, is energy is conserved. There's no such thing as energy, or there's no such thing as creating or destroying energy. It is what it is. All the energy that the Earth is composed of is what it is. Can't increase it, can't negate it. I mean, you can move it off from here to somewhere else.
Yeah.
But if you account for the whole system, everywhere anything could possibly go and add it all up, all that energy is conserved.
Okay.
And so I'll give you one more kind of deep insight into how to think about mass. We get to Einstein's famous equation, E equals mc squared. C there is just a constant, speed of light squared, doesn't matter. But notice what this says. It says energy is equal to, or is proportional to mass. So one more way that you can think about the mass of this marker, is it's somehow like the total of all the potential energy in here. If I could release all the energy from this marker, here's the equation that tells me how much energy that would be. When you split a uranium atom in half, the components have slightly less mass than they had when they were fused together. The mass goes down when you split a uranium atom in half. And so there's mass that's lost. What happens to that lost mass? Energy is conserved, so it just comes off as energy.
Okay.
Which is how a uranium power plant or an atomic bomb works.
Yeah.
They split uranium atoms in half. The two halves weigh less than the whole did, which means I have less mass than I started with, but energy is always conserved. So all that means is some of that mass went off as energy. Mass is just one more form of energy, is one way you can think about it. Mass is how much potential energy is in that thing. When I split that atom in half, I release a little bit of its potential energy into photons. So fundamental concept, fundamental idea, one of the most crucial things to understand in all of classical mechanics, energy is always conserved. There's no such thing as losing energy. Every joule ends up somewhere. It can always be perfectly accounted for. Make sense?
Yeah.
Okay, so let's jump over to this board now and just start doing a bunch of example problems. Of using all this. Let's get that a bit closer. And grab my book in case I need a reference in here of these. And we're not quite done covering new material yet, but that's basically all the new material. Okay, so let's start using these facts to solve some problems. So I've got a 0.145 kilogram baseball, and I throw it straight up with an initial velocity of 20 meters per second. The question is, how high does it go?
Okay.
Now we could use our kinematic equations to solve this problem. and we've already gone through and done that before. But now we can do it even easier using our equations over there. I know that the kinetic energy at the end, I know that 1/2 mv2 squared plus mgh, the height at the end. We'll call it y2 for a second. We'll just write it out. We'll do it very explicit the first time, and then once you get used to it, I'll start using shorthand. Y2 is equal to 1/2 mv1 squared plus mgy1. Right? My kinetic energy plus my potential energy, when the baseball's at its highest point, is equal to my kinetic energy plus my potential energy right when I threw the baseball.
Yeah.
Because from the instant I let the baseball go to the point where it reaches its max height, the only force acting on it was gravity, which is a conservative force. We're ignoring air resistance. Make sense?
Mm-hmm.
Okay, so let's calculate that really quick. What is my velocity at the second point when the baseball reaches its height? 0. And so now we just have mg. What's y2? Y2 depends on where I call how I decide my y coordinate system. But if I set my y coordinate system, so here I am throwing the ball up. That's terrible. Where's my eraser? We'll call, if I'm throwing the ball up, here's me, and I release the ball right here and it starts going up, I call the release point y equals 0, right?
Yeah.
So if I call that y equals 0 my release point, then this is also going to be y1 where it starts, right?
Mm-hmm.
And then y2 then is up here when it reaches its max point, which is just h, the height the ball goes. You see that?
Yeah.
Okay, so this is equal to 1/2 m, my velocity when I throw it squared. What's my potential energy at the start?
Your potential energy at the start.
Yeah, what's mgy1 when I throw the ball?
0.
It's 0. Now maybe we should have had this brief discussion with calculating potential energy really quick. Notice that potential energy somehow depends on my coordinate system. It has a y1 and a y2 in there, right? If I happen to call this point 0, so that my potential energy was 0 here. I could have also called this point 0, so that I had some potential energy here, and I had even more potential energy here. It turns out all that matters is, in both cases, they have the same change of potential energy. You with me?
Mm-hmm.
Because, let's think about it. Let's reset this problem. If instead I decide to call this point y equal to 100 and set up the same equation again over here,
Okay.
then it would have been, my gravitational potential energy at this point would have been mg times h plus 100, right? That's the height at this point.
Mm-hmm.
And then that would be equal to 1/2 mv1 squared plus mg times 100, right?
Yeah.
Now notice that when I distribute that through to the 100, I have mg 100, mg 100. Those cancel out from both sides. I'm left with mgh equals 1/2 mv1 squared,
Which is already what you have.
which is already what you have. So it doesn't matter what you call potential energy 0. It doesn't matter what you call your y equal to 0 or where you define your potential energy to be 0. Pick it where it's convenient. Because it turns out only the change in potential energy matters. It doesn't matter if we say you have a billion joules of potential energy here, and then some more here. All that matters is the change of potential energy. That's all the physics cares about. So, grab my eraser. So to calculate this problem, we just have to calculate h from this simple equation. We didn't have to use two kinematic equations, solve one for time, and then plug it into the other and get our conclusion that way. We just got this simple equation.
Okay.
And now, how do we solve it? We just solve for h. So then h is equal to m times v1 squared over, oh wait, m's cancel out from both sides, sorry. Divide both sides by m. So cancel that out with that, right?
Mm-hmm.
And so it's just v1 squared over 2g. And that might look familiar, because that's the exact equation we came up with when we were calculating how to get the height in general, except we used a v naught there. I know I've got my calculator somewhere. So now we can just plug in our numbers. We know what the initial velocity was. I threw it up at 20 meters per second.
That's all you need.
And it turns out the mass didn't even come into the equation.
Why not?
Cancel out from both sides.
I mean,
So why'd they give it to us?
yeah.
They probably reference that problem again in an example too. Sometimes they do stuff like that. It's annoying. So we have 20 squared divided by 2 times 9.8, which is, if we have 3 significant figures, 20.4 meters. Let me also pull up the example problem here, make sure we didn't make any mistakes. 20.4 meters. So yeah, H is approximately 20.4 meters. I don't think that was a mark I've used before. Was it? Anyways, so we just calculated the height. Good with the first example? All right, let's move on to the second one. So in the previous example problem, assume your hand moves while throwing the ball a half a meter. So let's understand what that means. So I start out with the ball in my hand, right? And then for half a meter, I'm doing work on the ball. After that half a meter, I'm done doing work on the ball, and the ball moves out of my hand. So I'm going to do work on it for half a meter and give it enough kinetic energy that it's going to kick off at probably still 20 meters per second. I'm not sure yet. Let's see. So in one, assume your hand moves 0.5 meters while throwing the ball. Find A, the force my hand exerts on the ball, and B, the speed when the ball is 15 meters up. So we're still assuming the ball leaves at 20 meters per second. So let's focus on A for a second. How much force do I have to exert for half a meter in order to make sure that after that half a meter, my ball is going to leave my hand going 20 meters per second? You see what we're asking?
Mm-hmm.
So I need the work I do on the ball. To equal 1/2 mv 20 squared, basically.
Doesn't it?
I need to do enough work on the ball that by the time I get half a meter up, it's got a velocity of 20 meters per second.
Does it want you to give the work, or does it want you to give the force?
Well, I need to calculate the force, but the force determines the work, but the work needs to equal this quantity, the work I do on the ball, because it's work that gives me the energy, right?
Yeah.
So how much work do I need to do to get that quantity? Let me not bother with numbers yet. So I need the work I do on the ball to equal 1/2 mv squared, right? And now the work that I do on the ball in this situation is going to be mg. I need to overcome gravity. Sorry, not mg. Just how much force do I need to exert? So we're looking for the force. And I need to do that over a distance of this distance. And I need that to equal 1/2 mv squared, right?
Yeah.
So I'm applying a force over that distance of 1/2 mv squared. And so, to get my force is going to be equal to, let's write it this way, mv squared over 2 times my distance, right? Sorry, no, because I also need to cancel out gravity. So my force needs to be enough to not only cancel out gravity, but to actually push that thing. Because if I just cancel out gravity with my force, the velocity is going to be 0.
Okay. Is that force the net force, or is it?
So let's rewrite this better. The work I do on the system is going to be equal to the system's kinetic energy plus the system's potential energy. So let's write out exactly how I have it over there, actually. It's just a bunch of the quantities are 0. So writing it exactly how we have it over there. I know that the kinetic energy at the start, plus the potential energy at the start, plus the work we do on the system, is going to be equal to the kinetic energy at the end, plus the potential energy at the end. How's that so sorry? With me so far?
Why does the end matter? We're just trying to find it with 0.5 meters.
Now the start is when I start moving the ball, and in this case the end is when I release the ball. So talk about a new scenario now.
Okay, so that's not like the other. That's not
Yep, ignore previous problem now.
Yeah.
Okay, so my kinetic energy at the start is,
0.
my potential energy at the start we can define to be 0.
Yeah. Going this system.
So then we got the work from other forces, namely me, the work I do, is equal to, and now we can say the work that I do is just going to be my force times my displacement, force times how far I move it.
Isn't that affected by gravity still?
Well, this is now just the work that I do on the system.
Where's the work that gravity does?
Gravity is accounted for in initial and final potential energy.
Okay.
Good?
Yeah.
So here all we care about is the work I do on the system. So if this is 1 kilogram, and I lifted 1 meter in the air, I did 9.8 joules of work. That's the work that I did. So the work that I did on the system then has to be equal to the kinetic energy at the end plus the potential energy at the end.
Okay.
Good? So the work that I do, F times D, has to be equal to the potential energy at the end, 1/2 m20 squared, plus the potential energy at the end, which is also going to be m times g times that same distance that we moved it, lifting it 1/2 meter. And you see this is where we're accounting for gravity. Because notice if I move that over onto this side, that becomes a negative.
Yeah.
So I have to do more work if I give it more potential energy. So we're accounting for gravity. See that? And we were interested in F here, right?
Yeah.
So F is going to be equal to m times 20 squared over 2 times d plus mg. So you can see my force has to be at least as big as gravity, and then some to give it the actual speed. And then we calculate that real quick. And notice now we need the mass, so that's why they give us the mass in problem 1 instead of problem 2. Drives me nuts. So we have 0.145 times 20 squared divided by 2 times our distance is 0.5. So that's this quantity, plus mg, which is 0.145 times 9.8, and we get 59.4 newtons. I don't know if it's two significant figures, just 59. Oh, that's example 1. Example 2, part A, because there's a part B, so 59 newtons. Okay, 59 newtons. So we did that right. So this comes out to roughly 59 newtons. So that's the force I need to exert on it. And now let's look at part B. Part B, find the speed of the ball when we're 15 meters in the air. So now we need to find the speed of the ball when we're 15 meters in the air. Let's see, how would be the easiest way to think about this? We can still think about this from the perspective of the work I do, this quantity here that I do is always conserved throughout this whole process. So I can now, let me just replace this with K3 and U3 so that we don't get confused. Where K3 and U3 now are when the ball is 15 meters in the air.
Okay.
So I was holding the ball. I start out holding the ball there. I end up holding the ball here. That's where I release it. So we're calling this point 1, we're calling this point 2, where I release the ball. And then point 3 is up here.
Why does 1 matter?
the kinetic energy at 1 plus U at 1. I'm saying kinetic energy at 1 and U at 1 is right here. And then this is right when I release the ball, is 0.2, which is what we just calculated for. So putting this back at 2. And then 0.3 is somewhere up in the air.
Wouldn't it just be 0 to just use 2 and not 1?
It doesn't matter which one we use is my point. Because the quantity is conserved. This quantity is equal to, because from the instant I let go of the ball, once I put this much work into the system, after I put the work into the system, gravity is now the only thing acting on it. And so once I put that work into the system, from there on out, the energy in the system is the energy in the system, and it's never going to change again. So once I put my energy into the system, however much energy is in there, we can use that to calculate the energy at any future point. It's going to be the same energy. So we just barely did from 0.1 to 0.2, right? Me doing work on the ball in between 0.1 and 0.2. 0.2 is where I finally release it and it takes off. That's what we just did here and calculate the force I have to exert on it in that period. But now we're going to see what happens up here at 0.3. So now we're going to look at 0.3 here. So this is also equal to 0.3 is equal to 0.3, 0.3, and then we'll erase the rest of this. So I know the force I exert. Well, look at this once again really quick. Kinetic energy at 0.1, that's still 0, right? Potential energy at 0.1, we're still defining that to be 0.
Yeah.
Okay. The work that I do on the system is going to be my force times my distance. We just calculated the force. So I can multiply that by d to get the distance, and then this is the net energy I put into the system. Right? So really quick, when I take that and multiply it by, what was it, 0.5?
Yeah.
0.5. I put 29.7 joules into the system. So this is 29.7 joules. That's how much energy I put into the system.
Isn't the distance going to be 15 meters?
Well, this is for the work I put into the system.
Oh, yeah.
The work I put into the system is, I exerted this much force for half a meter, and I put that into the system. From there on out, that is the energy in the system. There's no way for energy to get into the system anymore. No one's adding energy to the system. The instant I let go of the marker, all that happens is it starts converting kinetic energy into potential energy, and then potential energy back into kinetic energy. But the sum of the energy is zero. The change in the total energy is 0 from the instant I let it go. So here's how much energy I put into the system. That's the total energy in the system until it like hits the ground again or something like that. Until it interacts with something else. But in the meantime, gravity is the only force acting on it. Gravity is a conservative force. The energy in the system is conserved.
Okay.
So I know that the kinetic energy at 0.3 plus the potential energy at 0.3 has to be 29.7 joules. You with me? Okay. Kinetic energy in 0.3, that's what we're looking for. We're looking for 1/2 mv3 squared. We're looking for v3. We're trying to find the velocity when we're 15 meters in the air. You with me? Plus, what's our potential energy?
Potential energy?
Yeah. It's going to be mg times what's our height?
15.
15.5. Because we define potential energy to be 0 here, not where I release it.
Okay.
Make sense? That's going to be a gotcha in some of these problems.
Yeah.
Okay. So now I calculate the velocity. So I'm going to replace this really quick with just W, the work that I do. But we know what that is, right? And I'm going to replace this really quick with H, the height that the ball moves, which is 15.5 meters. What can we do for you?
I'm just wondering if you're missing anybody.
He's in Vegas.
Okay, thank you.
Okay. So, solving for V3 now, we're going to get, we'll do it so. 1/2 mv3 squared is equal to the work I put into the system minus the amount of work that goes into its gravitational potential energy, into overcoming gravity.
Yeah.
So we get v2 squared is equal to, divide everything by m and multiply by 2. So we're going to get 2 times the work I do divided by m minus 2gh. Did I do that right?
Looks right.
So plug all that in and then take the square root, and that should be our velocity. So 2 times the work that we do divided by our mass, 0.145, minus 2 times gravity times our height, which is 15.5 meters, gives us 106. Oh, but we need the square root of that. Square root of 106, and we get 10.3 meters per second, or if it's only 2 significant figures, 10 meters per second. So V2 is equal to the square root of this whole thing, which comes out to roughly, not V2, this is V3, sorry. Velocity of 0.3, velocity of 0.3. Comes out to roughly, no, I already lost my number. 10 meters per second.
That's a nice number.
Yeah. So there we go. We just calculate the velocity when the ball is 15 meters up.
What was h?
15.5.
Yeah.
So this was 0.5, and then this was 15.
Yeah.
Think you got it? Think you can solve a problem like that
With a lot of time, yeah.
with a lot of time? If you get this set up correctly, if you have a correct interpretation of that, the rest of this comes out pretty easily. The kinetic energy at the start, plus the potential energy at the start, plus the work that goes into the system, is equal to its kinetic energy and potential energy at any point into the future.
Yeah.
So let's try another one. Oh, example 3, just read. Okay.
That's what exactly?
I think it didn't have much of a problem to it, so we can just answer from reading it. A batter hits 2 identical baseballs with the same initial speed and from the same initial height at different initial angles. So we got a baseball player and he hits 2 balls. One ball goes like this, and another ball goes like this. He hits them both the same hard with the same speed, just at different angles. You with me? Prove that both balls have the same speed at any height h if air resistance can be ignored. So prove that the balls have the same speed. Well, first off, they're given the same amount of work goes into both of them. The baseball batter hits them the exact same hard.
Yeah.
Good? So since the baseball batter hit them the exact same hard, and since initially their kinetic energy and their potential energy is 0, then I have that the work the baseball batter hits is equal to the kinetic energy of ball 1 plus the potential energy of ball 1. And it's also equal to the kinetic energy of ball 2 plus the potential energy of ball 2, right? So we don't get confused with subscripts up there. Maybe we'll call it ball A and ball B. So here's ball A at some random point. Here's ball B when they're at the same height, right? And it says prove that when they're at the same height, they have the same velocity. The same amount of work goes into both of them. If they're at the same height, they have the same potential energy. So their kinetic energy has to be equal. So they have to have the same velocity. Pretty straightforward? If they're at the same height. notice that there comes a point where ball A is traveling slower than ball B. That's when it gets up here. When ball A is up here, it's traveling slower than ball B ever moves. Ball B never moves that slow, but ball B also never gets that high.
Yeah.
So let's think about this for a second. Is A moving faster here or here?
Moving faster.
Yeah. So let's just think about ball A for a second. Ignore ball B just to do some intuition checks. Ball A at this point, so ball A flies through the air making this path. Is A traveling faster here or is it traveling faster here?
It's going too fast.
It's going the same fast between here and here?
Yeah.
No. It's going slower. Intuitively, in the x direction it has the same speed, in the y direction the acceleration is downwards, so it's slowing down.
Oh.
By the time it reaches up here, at that point, it still has the same speed in the x direction, but its y direction velocity has reached 0. So the ball, the baseball, is slowing down, slowing down, slowing down, slowing down, speeding up, speeding up, speeding up, speeding up, and it hits the ground with the exact same speed that it left if you ignore air resistance. You with me?
Yeah.
Another way to think about that, kinetic energy is the measure of the energy due to your velocity. The more velocity you have, the more kinetic energy you have. Right? So as the ball gets higher in the air, the kinetic energy goes which way, up or down?
Does it get higher in the air?
Yes.
Kinetic energy goes down.
Kinetic energy goes down because it's going slower. What about potential energy? Does this potential energy go up or down as it gets higher in the air?
Potential goes up.
It goes up. So kinetic energy goes down, potential energy goes up. The net change is 0. Kinetic energy goes down at the exact rate potential energy goes up. That's the amazing thing. So the total energy is conserved. If the kinetic energy goes down, potential energy has to go up. If potential energy goes down, kinetic energy has to go up. So here, kinetic energy is going down, 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 while potential is getting up and up and up. Here, kinetic energy reaches its minimum, and potential energy reaches its maximum. And then the reverse happens. Our potential energy gets smaller and smaller, and our kinetic energy gets bigger and bigger.
But the speed is this.
Kinetic energy is the energy you have due to your speed. If kinetic energy goes down, speed has to go down.
Okay.
Because kinetic energy is proportional to your speed squared.
Yeah.
So this follows whatever the velocity does. Velocity is getting smaller, your kinetic energy gets smaller. One way to think about kinetic energy is it's the amount of energy it would take to stop that object. Is it hard to stop an object that's moving really fast or really slow?
Fast.
Fast. So it takes more energy to stop it. There's a lot of energy in its motion. And so it would take a lot of energy to, it would be really hard to stop it. You have to absorb a lot of energy to stop that thing. Right? Kinetic energy, well, it's kind of a combination. Let's think about, once again, dam. How does a dam work? So probably some of our electricity comes from Hoover Dam, I don't know. We're relatively close to it. So how does a dam generate electricity? Where does that energy come from?
Comes from the water spitting this.
Comes from the water. But why? So the water hits the turbine, which spins the turbine, which spins magnets against the wire, which causes the electrons to move. Okay. But how come that turbine is able to spin? Because water hits it.
Water is weight.
The weight of the water. What you're doing is you're taking, so a river is water flowing from uphill to downhill. Water is flowing downhill. As water is flowing downhill, its potential energy is going down. If its potential energy is going down, it has to be going into something.
Kinetic.
It's going into, a lot of it goes into kinetic energy. The river speeds up. If you're further down the river, chances are it's moving faster than it was higher up the river. So the water speeds up as it goes down, and some of its the water's just going to be heating up, some of it's lost to friction. But a lot of that potential energy just goes to kinetic energy. Kinetic energy is how hard it is to stop that water. That water collides with the turbine, and that turbine now has to absorb a lot of that energy that it was just hit with by the water. So that water collides with it, it causes that turbine to move and move and move. It starts the turbine spinning. So the fact that it flows downhill converts some of the water's potential energy into kinetic energy, and that collision of the kinetic energy, causing that water molecule to basically come to a halt, pushes that energy into the turbine, causing the turbine to spin. And the process goes on, making so that we are able to have energy. We are transferring the energy from that river all the way over here to shine our lights. Amazing.
Yeah.
Let's just do some more thoughts about this energy thing to help you see how it's all connected and doesn't go anywhere. Well, no, we kind of already did. I think that's enough. So just trying to make sure you keep in mind this quantity is always conserved and get some intuition for when one's increasing and one's decreasing. If this goes up, this goes down. If this goes up, this goes down. Because their sum is always the same thing. It's a constant. It's the total work that went into the system.
Yeah.
Okay. It's hard to get an intuition for this stuff, but once you do get that intuition, it's unbreakable, and it's so absurdly useful.
Is light, like, when it comes out, is that energy it's moving?
Yep.
Where does it go?
Those photons?
Yeah.
Some of them are reabsorbed by atoms, which causes electrons to jump energy levels and move around at higher orbitals, or not higher orbitals, in their orbitals, jump energy levels. And then that photon will fall back down in energy level, and it will again shoot off a photon. And that happens all the time, and that's how you see me. What happens is, here's one of my atoms, here's the center, here's the electron moving around it. We'll do the oversimplified version really quick. Light shines, in other words, a photon comes along and collides with that electron, giving that electron more energy. A more energy electron is at a higher energy level. Right? Now, turns out that's unstable. It's kind of like balancing a marble at the top of a hill, and if it gets a little bit of turbulence, it's going to fall back down. Kind of. And so that electron is going to get knocked up there, but then it's going to come back down to its initial energy level. So it's going to go up and down. And accelerating electrons produce photons. And so when it goes up and down, it shoots out a photon then with that frequency, which then gives it a particular frequency of light. And so I absorb that photon onto my skin, and it absorbs it and then re-emits it, and that photon goes into your eye, and you see this wavelength, which is why things have certain colors. That wavelength determines the color. And so that's how you're able to see me. Those photons came, collided with my atoms, excited electrons, then got de-excited, so they emitted photons that then went into your eyes.
Okay.
And so your eyes are now a little bit warmer. Where some of them go in, some of them also bounce off of your eyes. And so I can see your eyes. And so there could be a photon that bounces off my eye, that then goes to your eye, then goes back to my eye. I'm seeing the photon that came from my eye. So it's all conserved. The energy just moves around a bunch of places.
Yeah.
It never actually goes anywhere. And this is actually some of the scams that you'll come across out there have to do with creating so typically the way that we lose energy, when we have an inefficient system, what that means is too much of the energy is going to heat. So when you have your car, you also put oil in your car. That's to lubricate your car so that there's less friction, so that you don't lose energy in your car to heat. You don't want to lose it to heat. We try to do everything we can to avoid friction, to avoid losing energy to heat. Friction produces heat. Even in a wire, electrons traveling through the wire, there's good materials and bad materials. And bad material wires are wires that heat up. And that means that the electrons aren't able to flow through it very well. It's a bad sign. It means there's a lot of friction inside the wire, and the wire heats up. So even in electric systems, the same thing's true. A bad system generates a lot of heat. We're wasting a lot of energy to heat rather than having it do the work we want it to do. And so sometimes they'll try to sell you heaters, like a little space heater, and they'll tell you things like, oh, this space heater is way more efficient. Now, I've yet to have someone explain to me how this makes any sense. How do you have a more efficient space heater?
It's doing the job.
It's better at converting electricity to energy. What happens to the electricity, or it's better at converting electricity to heat? What happens to the electricity that wasn't converted to heat? If it was used by the machine, it was either converted to heat or it was wasted, and so it was converted to heat.
True.
Or you didn't use the electricity. I don't know how you make a more efficient heater. And I've yet to have someone explain to me how that makes any sense.
What if it makes more?
With the same amount of energy, energy is always conserved. That's impossible.
What if materials are different? So it reflects.
The energy has to go somewhere. So the electricity goes in. Okay, now where did it go? My heater isn't bouncing, is it? And doing work that way. Even then, if it's just bouncing, that's still got to ultimately produce heat. Where does it go?
We're putting more energy into it.
Produces more heat.
So energy efficient space heater.
An energy efficient,
Well-
one that doesn't produce as much heat. So it's less energy.
That's weird.
Yeah, you gotta figure it out. And I talked to an engineer who was promoting one of these things, and I had them try to explain it to me, and then they got puzzled. They're like, you know what? I think it just might be a scam. That we're way overpaying for this heater as opposed to this heater. So I don't know. Maybe it makes sense somehow. But it makes no sense to me how there's a more efficient space heater than another space heater. There's just one that converts the energy quicker, I guess. But that's not more efficient. It's not using less energy to produce more heat.
Why do some of them more heat and the others don't?
Maybe what?
Why do some of them have more heat and others don't?
Because it's using more energy.
So it's just the amount of energy.
So it's just the amount of energy it's using. I don't know. I don't understand a more efficient one. One that gives you more energy per joule that you put into it. So I have my power bill. Is there one where I spent the same amount of money on heating and got more heat
Yeah.
using a space heater? I could get it if you're like talking about gas versus electric heating. Okay. But when you're just talking about a more efficient space heater, I don't know how that makes sense. And I talked to someone who was doing, that's one of the things they did, and they were an engineer, got their degree in engineering. And they were completely baffled after they thought about it for a second.
Yeah.
Anyways, random side note. Where are we? Exercise 4. Kind of dragging our feet with these exercises. Example 4. All right, a 25 kilogram skater goes down a quarter circle. So we have a quarter of a circle ramp right here with radius 3 meters. Well, we'll just say radius R. We'll plug in numbers here in a second. And we've got our skateboarder. And our skateboarder, they're standing at the top of this thing. And then they're going to ride their skateboard down the ramp. So they're going to start with no velocity. They're going to ride their skateboard. Now they're on down the ramp. And let's see what we're after. There's our mass. Find the speed. So I need to find the speed the skateboarder has at the bottom. And then the normal force exerted on the skateboarder at the bottom.
Isn't that just weight?
Kind of. There's going to be centripetal acceleration. Centripetal acceleration.
Awesome.
Yeah. Okay, so we'll start with the first one. The first one's kind of the new one. The second one's kind of like make sure you didn't forget stuff from previous chapters. So let's do the first one. So first off, we're assuming frictionless skateboard. The skateboarder, there's no friction between the skateboard and the ramp. So gravity is the only force acting in this scenario, right?
Mm-hmm.
And so it's going to be conserved. So I know that their kinetic energy at the start plus their potential energy at the start is equal to their kinetic energy at the end plus their potential energy at the end. Right? Well, their kinetic energy at the start, that's a 0, plus their potential energy at the start, that's going to be mg times how high they are. We'll call potential energy 0, the ground right here, right? So how high up are they?
Stage.
Just r, the radius of the scene, right? Because from here to here is r. So mgr, that's our potential energy, is equal to their kinetic energy at the end plus their potential energy at the end. We define potential energy so at the end it's 0. That's how we set up our y-coordinate system. Right? Okay. Honestly, I think that is going to be the hard part of a lot of these problems. Is just this initial setup and making sure you know how to plug in your variables. From here, now it's just stupid easy. All we're looking for is their velocity. So writing this side of the equation first, I know 1/2 mv squared, their velocity at the end. So maybe we'll say v2. That should have been 2. v2 is equal to mgr. Or in other words, v2 is equal to the square root of, let's see, we need to multiply by 2, m's go out. So I'll just multiply 2gr. Good? And then that comes out to roughly, whatever it comes out to. When you want the square root of 2 times 9.8 times 3 comes out to 7.67. Let's see, how many significant figures did we have? 7.4, 7.67. Okay, same thing. 7.67 meters per second is their velocity or their speed at the end. Okay, now we need to calculate their normal force here at the end. So remember, the sum of their forces equals their mass times their acceleration. So what are all the forces acting on this person at the end? So let's draw a free body diagram for them at the end. They have their weight pulling them down, right? And then they have the normal force pushing up on them, and that's it. These are all the forces acting on them. The skateboarder at this instant right here. Good? Now we know that the sum of the forces on them, N plus W, is equal to their mass times their acceleration. So it's equal to their mass times their acceleration. Do they have any acceleration at this point? Yes, centripetal acceleration. Because they're traveling in circular motion.
Does that keep going?
It's the last instant that they still have centripetal acceleration.
So it's still technically on the circle.
It's still on the circle. Yes. And intuitively, you can think about this. If you go down on that circle, right as you even out, you're going to have a little bit of extra weight. So, their normal force plus W is equal to M times A. Let's write this out really quick. Their normal force minus mg, or plus their weight, is equal to their mass times, what's their acceleration now? It's going to be v2 squared over r.
The acceleration.
Centripetal acceleration. Going back to this equation, ACP is equal to v squared over r. We also wrote it as omega squared times r. We also wrote it as, oh, I can't remember the one with the period in it. This is going back to like chapter 4 probably.
Yeah.
No, chapter 3. So at the end of each chapter, it gives you a review of the most crucial equations. And A, they call it radial acceleration, I always call it centripetal acceleration. V squared over R, or they do that way of writing it, they don't have the omega squared R1.
Okay.
That's what we're talking about. When we were calculating acceleration for uniform circular motion, is when we first derived it.
Yeah.
Anyways, So the sum of the forces on them has to equal their mass times their acceleration. And I forgot what we were looking for. Oh, the normal force. So now the normal force is equal to m times our centripetal acceleration plus gravity. Oh, we know exactly what V2 is. Let me replug V2 in over there. So this is equal to m times V2 squared is 2gr over r, which is equal to m times 2g. Let's think about it that way. You with me so far? V2 is equal to this. So I just plugged in V2 squared right here. R's cancel out. So here's my V2 squared over R. So my normal force then is equal to that, m times 2g, plus this, moving this to the other side. So it's just 3 mg.
3 mg?
Okay. Over there we have m times 2g, or 2 times mg. And then we plus mg, which gives us 3 mg. So that skateboarder feels like they have 3 times their weight at that instant. Good? Okay. Next one. A 12 kilogram box is pushed up a 2.5 meter ramp at 30 degrees. It is given an initial speed of 5 meters per second and only makes it 1.6 meters up the ramp. Find the force of friction and the speed when it slides back down. Okay.
Did we do example 5?
I read ramp and thought we already did it. Assume the ramp in 4 wasn't frictionless and that his speed at the bottom was 6 meters per second. Find the work done by friction. Okay, so let's do that one. So, setting up, once again, our equations. I know that the kinetic energy at the start, plus the potential energy at the start, plus the work that goes into the system, is equal to the kinetic energy at the end, plus the potential energy at the end. Right?
Yeah.
Now for this scenario, we're redoing this scenario this time. We're just saying, and there's also friction. So there's going to be some work done on the system, and it's going to be negative work. Good? Okay. So my kinetic energy at the start is 0. My potential energy at the start is mgr. The work that gravity can potentially do.
Yeah.
So this is mgr plus the work done by friction is equal to the kinetic energy at the end plus the potential energy at the end, which is 0. So here's all we are worried about. Now we can figure out the kinetic energy at the end because it's given to us that V2 is equal to 6 meters per second. So ignore that V2. They're saying, now pretend that when he reached the bottom he was only going 6 meters per second. What was the force of friction? Or the work done by friction? Not sure which one. The work done by friction. Okay, so 6 meters per second is this final velocity.
Yeah.
So we can actually calculate all these numbers. We now have everything. But let's just try it one more way. M times G times R.
Plus the friction.
If we want this to be a positive number, I'm going to say minus the work done by friction. Because friction does negative work, right?
Yeah.
Okay. Is equal to 1/2 mv2 squared. So looking for the work done by friction, the work done by friction then is going to be equal to, I'm going to move this quantity over here and this quantity over here. You with me? So it's going to be m times g times r minus 1/2 mv2 squared. And now we can just plug that into our calculator, and we're done. So let's see, mass is 25, so I have 25 times 9.8 times 3 minus 0.5 times 25 times 6 squared is equal to 285. 285 joules. $285. That was example 5.
Yeah.
285. They said negative 285 joules. We decided to set it up so it was already negative. Good?
Mm-hmm.
Okay. So now, oh, I don't need the book looking at this. Now we're on example 6. Okay, so example 6 was we push, so we've got a ramp. We push the box, so it starts out with some initial velocity of 5 meters per second. And the box only slides 1.6 meters up the ramp. Our job is to calculate the friction, right? Yeah, find the friction. And then we have part B that we'll worry about after we find friction. Didn't we used to have a good eraser in here?
We got one downstairs.
Yeah, I thought we used to already have a good one up here though. Shoot. Anyways, so setting up the problem, we draw some ramp. And it was at a 30-degree angle, I think. Yep, 30 degrees. We've got a box at the bottom of the ramp. And it starts out by sliding up with a velocity of 5 meters per second. And it makes it, from there to there, it makes it 1.6 meters up the ramp before it stops. So our job is to calculate the work of friction on this ink. Okay, so our initial kinetic energy plus our initial potential energy plus the work that goes into the system is equal to the final kinetic energy plus the final potential energy.
Yeah.
Our initial kinetic energy is some value. That's going to be 1/2 mv1 squared, where v1 is 5, right? Our initial potential energy, we'll just define our y-coordinate system, so that's 0. Plus the work of friction. So this time we'll leave it positive to follow the book, but W is going to come out to be a negative number. Is equal to our final kinetic energy is what? 0, because the box stops right there and then it's going to start falling backwards. Excuse me. So that's a 0. And then our final potential energy, what's that?
Just n times g times however high that is.
How high is it?
It's not 1.6.
It's not 1.6. 1.6 is this distance.
So it's 1.6 times the sine of 30.
1.6 times the sine of 30 degrees. Perfect. And sine of 30 degrees is 1/2. So half of 1.6, or in other words, 0.8.
Yeah.
But we'll do, well, we'll just do 0.8. Why not? Right?
Mm-hmm.
And so now our work, which once again is going to come out as a negative quantity, the work of friction, because we left the plus sign there, is going to be equal to mgh, mg times 0.8, how high we went, minus 1/2 mv1 squared, right?
Mm-hmm.
And so we can calculate that and figure out the work done. So our mass was 12, so we have 12 times 9.8 times 0.8 minus 0.5 times 12 times 5 squared gives us negative 55.92, so they probably say negative 56. Comes out to negative 56 joules. Make sure we did part A correctly. we supposed to find the force of friction?
It's just F sub K.
Find F, the force of friction, not the work done by friction. Okay, we just found the work done by friction, we needed the force of friction. Okay, so this was the work of friction, the force of friction, and in this case is kinetic friction, times our displacement, which in this case is 1.6, is equal to the work of friction.
So just divide that by 1.6.
Yes, take the work of friction divided by 1.6, and that should give me my force of friction. So that divided by 1.6 comes out to negative 35 newtons. So F sub K is roughly minus 35 newtons. We call that the positive direction.
Yeah.
And this side they just put 35, of course. Okay, and now part B. Part B was find the speed when it slides back down. Okay, so now we're kind of setting up a whole new problem. The box went up like that, now the box is going to slide back down the ramp.
Yeah.
We're assuming same material, so the kinetic friction is going to have the same force. So we'll have the same friction sliding back down the ramp. So let's just set up a whole new scenario so that we don't get confused by anything. Our box is up here, and it's going to move down 1.6 meters. And we want to know its speed when it reaches the bottom. Now, question. Will its speed when it reaches the bottom, will it be greater than, less than, or the same as 5 meters per second?
It'll be the same.
It'll be less. We're going to lose energy going up to friction that we can't get back. And we're going to lose energy sliding back down to friction that we can't get back. If it came back down at the exact same speed, we would have gotten all the energy back out of the system, which we can't do because of friction. Make sense?
Yeah.
So our velocity better come out lower or we did something wrong. Okay. So now let me call this the start and let me call this the end. Once again, my potential energy, my kinetic energy at the start plus my potential energy at the start plus the work done on the system is equal to the kinetic energy at the end plus the potential energy at the end.
Yeah.
Kinetic energy at the start,
0
0. Potential energy at the start,
is mg 0.8
times 0.8, perfect. Plus the work of friction,
is negative 35.
it's going to be the exact same thing, minus 56 joules,
Oh, the joules. Yeah.
is equal to kinetic energy at the end, that's going to be whatever it is, that's what we're looking for. Potential energy at the end is going to be
0.
0. So here's our equation, we're just looking for the velocity, right?
Yeah.
So v2 squared is equal to, divide both sides by m, multiply both sides by 2. So if I divide this by m and multiply it by 2, then we're just going to have 1.6g. If I divide that by m, multiply it by 2, this I need to divide by m and multiply by 2. We're going to have 2 works of friction divided by m. Right?
Mm-hmm.
Do all that right? And then take the square root of both sides. It's going to leave me with that. So let's plug that in and see what we get. We want the square root of 1.6 times 9.8 plus 2 times the work of friction divided by the mass, what was that, 12? Is equal to 2.5 meters per second. Which we can accept that, right?
Yeah.
And 2.5 meters per second. That's what they got. Perfect. All right, let's now do one with springs. 5.7. Guess we can still some space on the whiteboard. Move the camera. Keep you readjusting.
That's right. Do it on a chalkboard?
have space. If I stay in this area right here, should be fine. Just take that eraser. Okay. Example 7.7. A glider with mass 0.2 kilograms sits on a frictionless horizontal air track connected to a spring. Okay, so now we're doing some with springs. The spring constant is 5, and we're stretching the spring 0.1 meters. Okay. So scenario. And then here's our mass M on spring, so it's on an air track here. Frictionless air track. We know that the constant for the spring, K, is 5 newtons per meter.
Newtons per meter.
Yeah, spring constant is newtons per meter. So to calculate the force, it's equal to the constant, well the negative, but the constant times how far you stretch it, how many meters you stretch it, x. Which is in meters. So if this is 5 newtons per meter, and I stretch it 1 meter, the force must have been 5 newtons. If I stretch it 2 meters, the force must have been 10 newtons, etc. So, yeah, the units of spring constants are newtons per meter. Anyways, and this thing has a mass of 0.2 kilograms. Okay? We pull the glider, stretching the spring 10 centimeters and release it from rest. The glider moves back to equilibrium position. What is its velocity at 8 centimeters? Okay. So here is where the spring naturally wants to be. This is x equals 0.
Okay.
We've pulled it back here. So this is 0.1 meters.
Yeah.
Sorry, my picture's going to be a little bit ridiculous, but we need a little bit of space. So here's where the spring naturally wants to be. This is 0. We've stretched it 0.1 meters and we release it. We want to know its speed when it's over here at 0.08 meters. My picture's lying a lot, but
Yeah.
I think you understand the problem, right?
Mm-hmm.
Okay. Once again, it's completely frictionless, so the only force acting on this is the spring, which is a conservative force. So kinetic energy at the start plus the potential energy at the start is equal to kinetic energy at the end plus the potential energy at the end. Right?
Mm-hmm.
So I'm going to call this the start, this the end. What's the kinetic energy at the start?
Start is 0.
0, because I'm pulling this out, I grabbed it, I pulled it like that, and then I release it. So when I release it, the kinetic energy is 0. Plus the potential energy at the start
Is energy.
no, 1/2 m, or not m, 1/2 k, x, we'll call that x. This is at the start, x1 squared. So this is my x1, this is my x2.
Okay.
Right? Potential energy in the spring, we calculated over there. And this is equal to the kinetic energy at the end. 1/2 mv2 squared plus the potential energy at the end, which the spring still has potential energy, right?
Yeah.
It's not completely back to its normal resting place. So plus 1/2 k x2 squared. Follow that? So now we're looking for the velocity.
Yeah.
So I'm going to move this quantity to the other side. So I know that 1/2 m v2 squared is equal to, this is x2, this is x1, is equal to 1/2 k x1 squared minus 1/2 k x2 squared. Right? Multiply everything by 2, gets rid of all my 1/2s. And divide everything through by m. and we get v2 squared is equal to m over k. I'll just factor out the m over k out of all of this. x1 squared minus x2 squared.
Why isn't it k over m?
Because it is. Thank you. Okay, square root both sides. And there's our value.
Yeah.
All right. And make sure we did nothing wrong. We are looking for the square root of k was 5 divided by m was 0.2 times x1 squared, 0.1 squared minus 0.08 squared. Gives us 0.3. 0.3 meters per second, minus 0.3 meters per second. That's a good catch. So this was plus or minus. Velocity is equal to plus or minus when you take the square root. And it's, in our case, the negative case, because we called that way positive. So the velocity is in a negative direction. Make sense?
Yeah.
Okay. So, just the next problem. 7.9. Oh, 7.8. That one's not that different. Let's go 7.9 because it combines both. Okay, so 7.9, we're going to have springs and potential energy. 7.9, we've got a big elevator. So what's happening is we've got some big elevator, and we intentionally cut the cable. We're testing the braking mechanisms on an elevator to make sure it's like safe. So at the bottom of an elevator, there's a big, massive spring that compresses that the elevator lands on to deaccelerate it when we cut the cable. So I had a cable here, we cut the cable. And when the cable gets cut, the elevator also has some hooks that fling out into the wall to generate as much friction as possible. So it has some things that pop out to generate as much friction as possible to create friction to slow down on the elevator. And it also has that spring at the bottom to stop the elevator. So we're going to have some elevator, and it has a mass of 2,000 kilograms. Not 2,000 kilograms, sorry. I wrote 2 kilograms because K is 1,000.
Yeah.
2,000 kilograms. Okay. We'll say M. So it has some mass M. We'll make note M is equal to 2,000 kilograms. Let's see. The elevator, by the time it hits the spring, it's moving down at 4 meters per second. So we cut the cable. By the time it makes contact with the spring, it's going 4 meters per second downwards.
Yeah.
The safety clamps up here create a force of friction of 17,000 newtons. So the force of kinetic friction is 17 kilonewtons, 17,000 newtons. And let's see what else we're missing. The spring is intended to stop compressing, to stop the elevator compressing 2 meters as it does so during the motion. What is the necessary force constant K of the spring? Okay, so as the elevator hits, the spring is going to compress 2 meters.
Okay.
That's our intent. Our job is to figure out what would the spring constant K have to be in order to stop this elevator. So I don't know, we're some engineer, we're supposed to figure out what kind of spring we need under this elevator. This is safety regulations, it needs to be able to handle this situation. What kind of spring constant do we need to place there to make sure that the elevator passes this whatever regulation? With me? Okay, so there's our picture at the bottom. We'll start throwing some math up at the top. Once again, always and forever, the kinetic energy at the start plus the potential energy at the start plus the work that goes into the system is equal to the kinetic energy at the end plus the potential energy at the end. Right?
Yeah.
Okay, kinetic energy at the start is, it has some, it's going to be 1/2 mv1 squared, where v1 is 4 meters per second. Right?
This is when it hits the spring?
Yeah, we're talking about the instant it makes contact with that spring.
Okay.
Plus, we are going to have potential energy. It has gravitational potential energy. And it has 2 meters of it if we call, when the spring stops compressing, if we call that U equals 0, our potential energy 0 for gravitational potential energy.
Yeah.
Right? So it has N times G times 2 for its gravitational potential energy. Plus its spring potential energy is 0. The spring's completely uncompressed at that point. It has no potential energy. Is equal to, what's our kinetic energy at the end?
What about friction?
Oh, thank you. Friction. Plus the work done by friction. In our case, we know it's going to be the force of friction. It's going to be minus the force of friction times 2, right? Good. Is equal to, what's our kinetic energy at the end when it comes to a stop?
0.
0. And then we just have spring potential energy after that.
Yeah.
Our gravitational potential energy 0, and we just have spring potential energy, which is going to be 1/2 times our spring constant times our x squared, and our x in that case is going to be 2. It's going to be compressed 2 meters. And we're looking for the k. You with me?
And you have all the numbers.
And we have all the numbers. So multiply through by, we'll call this 2 squared since we've already plugged out in 2 other places. So actually one of these 2's cancel out with that, so that cancels out with the 1/2, and we just have 2k. Now divide through by 2.
Yeah.
So we're going to have n times v1 squared over 4 plus mg minus f sub k is equal to k. Right?
Yeah.
And so, away we go. So we have the mass, 2,000, 1, 2, 3, times 4 squared divided by 4 plus mass, 1, 2, 3, 2,000 times 9.8 minus 17123 is equal to 10600. So this is equal to 10600 newtons per meter. Find our book. Where do you have it? 1.06 times 10 to the 4. 1.06 times 10 to the 4. Same thing. Okay, so we found out the constant of that spring. Good? Okay. That was pretty easy. Let's look at 7.11 instead. That one looks harder. A region of space. In a region of space, the force of an electron is given by c times x in the j direction. So I'll write it out how they write it out here in case you forgot this kind of notation, and then we'll re-explain it. So they say the force on an electron is equal to some constant c times x we'll get into the x here in a second, times j hat.
Yeah.
Okay? Remember that this is saying the exact same thing as 0, comma, c times x, comma, 0. Same thing, right?
J is y.
Yeah, it's your unit vector in the y direction.
Yeah.
Okay. Anyways, just want a quick reminder of that thing. And now, so that's the force on the electron. The electron moves around a square loop in the xy plane. Calculate the work done on the electron by the force F during a counterclockwise trip around the square. Okay. And then question, is the force conservative? So here is some circuit in the xy plane. And the electron starts right here. It's going to travel around this circuit and go back where it started. Now here's our equation for the force on the electron. Here at 0, when we're calling this our xy plane, so this is x equal to 0. And we'll call this x equal to, I think they used an L for how big it was. Yeah, L. And this is also y equal to 0. This is y equal to L. So here's our coordinate system. This is x. This is y. This is L. And this is L to square. You with me?
Yeah.
Electron moves in a circuit around here. Question. What is the force of the electron at this point? What's the force on the electron at 0, 0? Here's our force vector at any point. What's the force at 0, 0? 0. Right? What's our force over here at L?
0.
No. What is our
Why is-
x?
There's your force vector doesn't have anything for x.
Okay. So my force in the x direction is 0. What's my force in the y direction?
It's just CLJ or CJ.
C times L.
CL.
C times L. So right here, my force is like that, in that direction, right?
How did it get to L?
Doesn't matter. We're being told that the electron's moving in this circuit.
Okay.
So how it got there isn't part of the question. But the point is, when the electron's here, the force on it is C times L.
Okay.
When the electron's here, halfway there, the force on it is half of C times L. In the y direction.
And how does it move this way?
And it has no force in the x direction, it has no force in the z direction. We'll ignore the z direction altogether and pretend this is two-dimensional. So the electron moves around the square, and this is the force on the electron by some electric field at any given point. So the force here would be like that, the force here would be like that, right?
Is that the net force or just the single force? Because how does it get to L?
The force is changing. This is just the force from an electric field.
So other stuff's affected.
So there could be other things at play here.
Okay.
We're just going to calculate the work done by the electric field on this thing.
Okay.
So the electron starts out here, travels to here, travels up this thing. What's the force on it here?
So CKL.
Still C times L, so that's still going to be like that. And then it's going to be half that right here, and it gets smaller right here. Here, it's always 0. All the way down here, it's always C times L. So what was the total work done on the electron? The total work done on the electron is going to be the work that was done on going from here to here, plus the work that was done on going from here to here, plus the work that was done on going from here to here, plus the work that was done on going from here to here. Okay.
So you want to do integral for them?
Yeah, wondered if that was the right way to do this. From point 1 to point 2, the work done on the second leg is let's see what they say here. On the leg from that to that, the force is everywhere perpendicular, so it's 0. The work done on the first leg is that. The force has the same value, blah, blah, blah. Yeah. So we'll just make arguments about 3 of them and then show the only one that we care about. The work that this force does, going from this point to this point, has to be 0. Because the work is perpendicular, or the force vector is perpendicular to which way the electron's moving. Right? When I lift this chalk and I walk this way, gravity does 0 work. Because gravity is perpendicular. It's not moving in the direction of gravity.
Does 0 work?
Gravity does 0 work on this when I walk in the x direction. When I lift it, gravity does negative work. When I drop it, gravity does positive work.
Okay.
Or another way to think about it, how do we calculate work? It's a dot product, which means you times by the cosine between them. What's the cosine of 90 degrees? 0. So work comes out to 0. So the work is 0 here. So on this branch, the electric field does 0 work. On this branch, the electric field does 0 work. The electric field is 0 right here, so it does 0 work. So the electric field only does any work right here.
Okay.
So our work is going to be the integral from 0 to L.
0 to L.
We're talking about in the y direction. Now y we start out at 0.
So that's 0.
Uh-huh.
Okay.
And then we end up at L.
Mm-hmm.
Of our force, what's our force over here? Our force is C times L times dy.
Yeah.
You with me? I just calculated the dot product. So here's what is in general. Work is equal to the integral from point 1 to point 2. In our case, we're going from here all the way around back to here. Of our force dotted with our displacement vector, right?
Yeah.
It's 0 here, it's 0 here, 0 here, so all we care about is this branch of the leg. So in that case, we're just going to go from 0 to L. When we take this, well, we'll say point 1 to point 2 still calls point 1, point 2. But it turns out all we care about is from here to here, so we'll say that this is P1, this is P2. But when we calculate the dot product, this is equal to the integral from F dotted with dr. F only has a component in the y direction. So it's going to be this dotted with dy. So it's going to be c times x dotted with dy. The x on this entire branch of the journey is just L, a constant, it doesn't change. And so since we're integrating with dy, how does y change? It goes from 0 to L. There's all the thinking I should have probably gone through. Okay. So that's how we got that. Good? Okay. So now we take the integral, and what do we get? We get c times L times y, evaluated from 0 to L, which gives me c times L squared. So there's the work done by the electric field if the electron starts at this point and ends at this point. Question, was the electric field a conservative force? No.
Because it came back.
So non-conservative force.
Yeah.
And CL squared. So we did that right. And work done by friction. I don't think we need to do that one. Okay. Force now and potential energy. Let's notice a relationship really quick. In calculating potential energy with gravity, here was a potential energy from gravity, right? We started out with our force vector, and we integrated it. We started with our force vector, and we integrated that along some path, which gave us our change in potential energy, but gave us our potential energy, right?
Yes.
So if integrating, notice we did the negative of the force. When we integrated the negative of the force, that gave us a potential energy. Similarly over here, when we integrated the negative of the force, that gave us the potential energy. Yes. Of the force acting on it, it gave us potential energy. So, oh, sorry, we're off the camera. Come back over, stay over here for a second to make sure we don't go off the camera. So, when I calculated potential energy, I calculated it this way. I did an integral from A to B of negative, when we talked about gravitational potential energy, it was negative mg, negative the force of gravity, dot dr, or in our case, dy, right? And this gave us our change in potential energy. Similarly, when I wanted the potential energy of a spring, from A to B, it was negative kx times dx. And this gave me my change in potential energy of my spring.
Yeah.
So integrating the negative of the force gave us our potential energy. So the next thing that they point out is simply that if you take the derivative, well, with respect to, how are they going to say it? Just the distance, I guess. Notice in both these cases, this one happened to be in the x direction, this one happened to be in the y direction. But they're both just in one direction. So pretend that we did it, both of them in the x direction. So when we take the derivative of potential energy in the x direction then, it gives us the negative of our force in that direction.
Okay.
That's all they were pointing out.
Yeah.
Which is pretty obvious, right? Because once again, just manipulating this expression, we get du is equal to negative f of x dx. We integrate both sides, and we get u is equal to, well, that integral, which is exactly how we got u. Now that's an indefinite integral. We got u from, we did with a definite integral, so don't be confused by the fact that we got a u there and a delta u there. It's just because this one's going to be indefinite.
Yeah.
Okay, so you take the derivative of potential energy and it gives you, and you can get back your force. I don't know if I'll give you any calculating partial derivatives, so we won't get into that. Yeah, partial derivatives, it's a Calc 3 concept, but it's really not that complicated. We can cover it if we need to, but for the time being, I think we'll just not do it. If I gave you any that have partial derivatives, let me know. You'll know a partial derivative because it will look like this. If you were told to calculate the partial derivative of u with respect to x, then that would look like this symbol. So that's if you're calculating the partial derivative. The derivative of u with respect to x looks like that. That's a partial derivative. I don't think I give you any problems working with partial derivatives. If I do, let me know and skip it. You don't have to do it.
Okay.
It's a Calc 3 concept. It's not super hard. It's just we didn't cover it. So we'll just do 7.13 since that doesn't have it. An electrically charged particle is held at rest at some point x equal to 0. A second particle with equal charge is free to move along the positive x-axis. The potential energy of the system, u of x, is equal to c over x, where c is a positive constant that depends on the magnitude of the charges. Derive an expression for the x component of the force acting on the movable particle. Okay, so they gave you a lot of words there, but this is actually a fairly easy problem. They said, you've got some system with two particles. The potential energy between those two particles, u, they said is some constant over x. Okay. So how does the system look like? We have one charged particle right here, and we have another charged particle right here. This charged particle is somehow fixed, it can't move. This one's free to move. Right? And if this happens to be a positive charge and a negative charge, if it happens to be that way, then moving this particle this way increases its potential energy because it naturally wants to fall this way. Positive charges and negative charges attract.
Yeah, farther away.
Yeah, so the further away I move it, the more it can fall back. The higher I lift this, the more it can fall back. So this one can't move. This one's fixed. This one's free to move.
Is this like magnetism?
Sure. It's like it. We haven't covered exactly what charges are yet, we haven't done anything with charges yet, but the point is, you know that opposite charges attract, right?
Yeah.
So if this is positively charged and this is negatively charged, this naturally wants to move towards that, right? And we can get energy out of the system if it did that, right?
Yeah.
Same way I can get energy out of this thing falling as it moves towards the Earth. Think about this is the Earth and this is my piece of chalk. Same principle. As it moves towards it, we can get energy out of it. If I want to move this particle away, I have to put energy into the system.
Yeah.
It's hard to move it away, and I can get energy out of the system, letting it move back. If they're positively and negatively charged. So we're saying the potential energy is C over X, where X is the distance between them. So let's see, maybe they have a positively charged. They're saying if we make the distance really small, then the potential energy gets really big. So they're actually saying that they're both positively charged. Sorry, should have thought about it first. Positively charged. They have the same charge. I don't know if it's both negative and both positive, but they both have the same charge. So now it's inverse. Because now this naturally wants to push away from each other, right? It's like backwards gravity.
Okay.
In other words, if I take this particle and I stick it right next to it and let it go, it's going to fly that way. So it's putting energy in the system, moving it closer, getting energy out of the system if I let it go. You with me? So we're saying here's the potential energy between them. It's some constant, like mg, some constant, divided by the distance between them. If the distance between them gets really, really small, if I put them really, really close together, then the potential energy is really high.
Yeah.
Because if I pull that, force that to be really, really close and let it go, that bad boy's going to shoot off. So we can get a lot of energy out of it. So here's the potential energy. Now they just want you to calculate, okay, so what's the force going to be that you'd be fighting? This f of x. And f of x is just negative the derivative of u with respect to x.
Yeah.
So when we take the derivative, remember this is the same thing as c times x to the minus 1, right? Bring the minus 1 down and subtract 1. So negative and negative makes it positive, so it's going to be c of x to negative 2. C over x squared, which is the same thing as c over x squared.
Yeah.
Which, notice that actually it didn't come out negative in this case, so the force is actually pushing this way, which makes sense because they're both positively charged. They both have the same charge. Okay. That's it.
That's it.
That is it. Yep, that's it. So, any questions on anything? Okay.
Later.
Yeah, the rest of the class for homework, and yeah.